Hello everyone, I want to welcome you to today's lecture. Emeka Udenze once again is speaking. In today's lecture, we'll be talking about the classification of matter as we continue in this lecture series. Let us take it from there. So at the end of this lecture, we're going to be learning the flowing about. We'll be able to describe matter with examples. We're able to classify matter based on its composition. I think there's a mistake here. I'm going to make a correction. Yeah, based on its composition into pure substances and mixtures. And also, we're able to classify matter again based according to each state and illustrate the three states of matter, which is the solid, the liquid, and the gas. So we classify matter in two places. We also represent elements and compounds using chemical symbols. And then we'll be able to describe the differences between physical and chemical changes. And finally, we'll talk about the law of conservation of matter, which is very, very important for us to understand. This law guides chemical reactions. All right, let's take it away immediately. So let's start with classification of matter. To make this briefly, I was able to make these graphics for the classification of matter. So matter is the big umbrella here. So matter is classified into two broad categories. The first category is matter is either as a pure substance or as a mixture. Now let's start with mixture. A mixture is a physical combination of two or more substances. Physical combination of two or more substances. There's no chemical interaction here. So because it's a mixture, the composition of mixture varies. It varies. The composition of mixture varies. And because the composition varies, because there are a mixture of different substances inside, the properties also varies. So if you get a sand, inside a sand, a good example of a mixture is a sand, right? Inside the sand, you're going to see gravel, you're going to see dirt, you can see some dry leaves, you can see different stuff in it. So it has different stuff which retain their own properties. Most importantly, you can actually separate a mixture. A mixture can be separated by physical method. So what you simply need to do is to begin to isolate some stuff from one another. You can actually take it apart, take a solution apart, and without any chemical means. You don't have to do any type of chemical reaction, and then you'll be able to separate the mixture. So a mixture is further divided into two parts. All right? A homogeneous and a heterogeneous mixture. But before we talk about that, let's now pivot over to the other part of, remember I said matter is divided into two, the mixtures and pure substances. So let's talk about a pure substance. A pure substance has a constant and definite composition. The composition of a pure substance is constant. It will never vary. If you have a water molecule, which is in this case a compound, there will always be 2:1 ratio of hydrogen to oxygen. It is constant. Because it's constant, it has a fixed set of property. The property does not vary. Because it's one thing, it has a pure substance contains one stuff, only 100% of that stuff. So the property is just the properties of that stuff and will never change. And if you can actually break it, it has to only be broken down by chemical means. You can only use a chemical means to actually break it down. Those chemical methods can be time consuming and has to take energy, right? And like I said again, it has only one substance inside it. It has only one substance present inside it. Only one stuff present. Now, under each of these two broad classification of matter, which is between mixtures and pure substances, you can break it down further. So to break it down further, mixture is broken down into homogeneous and heterogeneous mixture. I'm going to move this a little bit up. So let's talk about that. So a homogeneous mixture is a mixture that have the same properties throughout and has only one visible phase. In other words, it is very uniform in another way. And a common examples of those, I'm going to list some of the examples, is if you have a sugar solution a sugar solution in water, you're not going to see the sugar. You're just going to see something water. You have an apple juice. An apple juice is another good example here. An apple juice. You have other solid solution like a steel. A steel is made up of iron and carbon, graphite. Salt water as well. If you dissolve salt in water, salt water is very uniform. You're not going to see any different layers. On the other hand, a heterogeneous mixture is a mixture whose property varies throughout. By the look of it, you're going to see a significant difference in the properties. And you're going to see many phases, that it has more than one physical phase in it. Common examples is an interphase, or rather a mixture of oil plus water. If you mix oil and water together, you're going to see that layer of separation, because water is polar, oil is non-polar. They're going to try to separate. Another thing you can see here is your salad dressing. If you can look at your salad dressing, it is trying to always separate if you keep it standing. Again, sand and water. If you mix sand and water, it's easy. You can easily see the two layers. The sand will separate down, water will remain up. And maybe common once again is the trail mix. Trail mix, when you eat your trail mix, you see all the nuts there can easily be separated because they are in different, you can see them visibly. They are not very heterogeneous. Then we'll now move on the other side. The pure substances, on the other hand, is broken down into two broad categories, which are the elements and the compounds. All right? So elements are actually those units of atoms that cannot be broken down into simpler substances by chemical or physical method. If you keep breaking it down, you're going to get to a point of a matter where you cannot break it down anymore. In this case, that point will become one atom of that element. You cannot go further into it. Now, there are about 118 of them that exist that are located in the periodic table, and they form the building blocks of all matter. They are the building blocks. Every matter is built from elements. Example, again, I wrote H2O. In this case now, there are two atoms of hydrogen and one atom of oxygen that come together in that chemical association to form the compound, which is the other side we're going to be looking at. But common examples of elements are sodium. Well, sodium is a single element. Oxygen exists as a homoatomic molecule. Hydrogen, copper, these are all examples of elements. And again, these elements can be found in the periodic table. What about a compound? A compound, on the other hand, is a chemical combination of two or more elements. There has to be a chemical union between two elements. Just like I give you an example again, to form a compound. They can only be broken down. They can only be separated by chemical means. It takes time and energy to break them down. It's not through physical. You have to do some chemical trickery there for you to break it down. And one thing here is that they have a definite and a constant elemental composition. Again, here I told you about water. There has to be two hydrogens to one oxygen to form a mole of water at any point in time. Common examples here include water molecule, carbon dioxide, sodium chloride. A good example again, even sulfuric acid. Now, like I said, they have common elemental composition. Here, for hydrogen, there's two atoms of hydrogen to one atom of oxygen to make water. In carbon dioxide, one atom of oxygen to one atom of carbon to two atoms of oxygen. In sodium chloride, one atom of sodium to one atom of chlorine to form that. And in sulfuric acid, two atoms of hydrogen, one atom of sulfur, and four atoms of oxygen to make up that sulfuric acid, which is a compound. So this is a brief way we classify matter into pure substances and mixture. So let's just break down, provide more context about elements. So elements, of course, like I said, they are pure substances, of course, that cannot be broken down into other substances by either chemical or physical means or method. Now we have about 118 of them located in the periodic table. And common examples are the iron, aluminium, oxygen. These are common ones we see every day. Hydrogen. All matter in the universe contain element. What it simply means is that they're actually the building blocks. Mother's elements are the building blocks of matter. The building blocks of matter. Of course, some matter are made up of homoatomic molecules. Homo means they have the same atom, but in this case, they just exist naturally beyond just more than one atom. So some of these, there are 7 of these guys in the periodic table, and they are hydrogen, H2, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So this molecule does not exist as individual atoms, but rather they exist in association with atom of itself to form homoatomic molecules. So these occur as homoatomic, diatomic molecules. Now, whereas others themselves, particularly the metals themselves, particularly exist as individual atoms. Good example, sodium, potassium, zinc, iron, uranium, and lead all exist as individual atoms of the element in the periodic table. So this is a closer look of the kind of periodic table we're going to be using in this class. So of course the periodic table is broken down. We're going to be talking about the periodic table, I think, in about few lectures from now, broken into groups and then periods, but that's not what we're going to be talking about now. What I want to show you now is that each of them this is the library of all the elements that form the building block of matter. As you see here, each of them have their symbols, they have their name down. Oh no, I didn't get that correctly. So they have the symbol hydrogen, they have their name down here, and then you now begin to go down to see all the rest of them. So this is the periodic table of element that contains all those examples. So the 118 of these guys in the periodic table. Yes, so this is an important document that we're going to be using in this class on how actually to read and interpret this periodic table will be an important skill that we need to learn in this class. So let's start with a reflection here. It says classify the following: hydrogen gas, fluorine gas, hydrogen fluoride gas, seawater, sand, air, sodium, chalk, water, and phosphoric acid using the classification scheme. So which is this classification scheme? Remember, we use this, but the broad classification is matter is broken down to mixtures and pure substance. Under mixtures, we have homogeneous and heterogeneous, and under under mixture, we have homogeneous and heterogeneous, and under pure substance, we have element and compound. So let's start there first of all. So let's start with pure substances. Let's see. Looking at this is a pure substance because that is the atomic element hydrogen. So H2, F2, HF, which is a compound. Which one again? So this seawater is not, sand is not, air is not. Okay, sodium. What else? And phosphoric acid. I would say phosphoric acid. So H3PO4. These are all pure substances. They're all pure substances. That's how you classify these ones. Whereas on the other hand, we're going to classify the mixtures. I'm going to use a different color. To classify mixtures, seawater is definitely a mixture. Seawater is a mixture of different stuff. Sand, of course, is an obvious one. Air, the air we breathe is a mixture of different gases. Chalk water, these are all mixtures. Yes, so that's the broad. What about the, let's break it down into more other classifications, into smaller classifications. So here we know pure substances are broken down into element and compound. So which ones are element here? Which ones? So let's break down. So into element, let's see which ones are element. Okay, let's start. Elements: hydrogen, fluorine, sodium. Okay, those are all the elements we have. These are the elements. Whereas the compound will be the one that contains more than one element. Fluorine, hydrogen fluoride, and then phosphoric acid. Both are compound. So we've broken our pure substance into element and compound. Now what about the other ones? What about our mixture? Of course, we can break down our mixture into homogeneous and heterogeneous. So let's start with the homogeneous. Homogeneous, of course, will be seawater. Seawater is very homogeneous. You can barely see any difference in anything. Air itself will be homogeneous. And then after that, we've isolated both seawater and then air. But the rest, which is chalk water and sand. So sand and chalk water are heterogeneous. So you should be able to use this classification scheme to classify matter either with a broad classification of mixtures and pure substance, or further breaking down the mixtures into homogeneous and heterogeneous, and the pure substance into element and compound. So let's talk about the symbols of element now that we're talking about element, right? So every element is represented, has a unique name, of course, and a unique symbol that represents that element. Most of those come from either the elemental properties or derived from names of former scientists, places, astronomical bodies, or mythological characters. So there's usually different ways you can name this thing, either from the property, where it was discovered. So there is always a method towards this type of nomenclature. And most of them, like again, here hydrogen, look at it, hydrogen is H. You know, that's the English name H, comes from there, right? But if there's another one that starts from H again, like you say helium, in this case, we can't put H there again, that will overlap. What you do in this case, remember here is uppercase H. You have an uppercase H and the next letter that follows it, which is E, and you have HE. So that is how they come to that nomenclature. Because hydrogen has already taken H, so the next one that starts with H has to have the second letter, but this time a lowercase. A good example of this one again is boron. One of the early elements takes B, right? So then other ones are derived from their Latin names. Example is silver. Silver is represented by Ag. Where did that name come from? Ag, it came from argentum. So it's a Latin word. Argentum is a Latin word. That's why we say argentum. Now some other ones are derived from the names of popular scientists. Example, what about this element? Istantinium. Istanium. Derived from, which is Es. Where does that come from? Derived from the name Einstein, and that is in honor of Albert Einstein, one of the greatest scientists that ever lived. So Einstein. So Istanium from Einstein. What about europium? Europium, of course, this is common if you know where this comes from. I think it was first isolated in Europe, EU. This was first isolated in Europe. So that is derived from the region or the continent Europe. And then we also have plutonium, Pu derived from the name Pluto, which is the planet. So there is a method to the nomenclature of all these elements we find in the periodic table. So those names came from, like I said again, famous scientists, places, astronomical bodies, or mythological characters. So, and it's important for us to understand how this organization begin to be. By the time we begin to work on the periodic table, this is going to begin to make sense more. So each element, like we said, has its elemental symbol, right? And the formula. And like I said, since they're derived from the names of the element, and first, they have to consist of a capital letter, or what we call the uppercase letter, or an uppercase letter followed by a lowercase letter, right? As shown in the periodic table. Let's see an example. This is the periodic table representation. This is the periodic table notation. This is how the periodic table represents this. So fluorine, in this case, this is the elemental symbol, fluorine F. The atomic number or the serial number is on top. The name is written under the symbol, whereas the other number is what we call the atomic mass. The relative atomic mass is also written there. So this is how they are written in the periodic table. Like I said, the elemental symbol is in the middle. You have on top of it the atomic number, then the full name of the element, and then under the full name of the element you have the mass of the element. So the same thing goes for this, and the same thing goes for this. So how do we now put that into a compound formula? A compound formula consists of symbols of atoms that make up the molecules or the formula unit, or the compound. So each elemental symbol represents one atom. Each elemental symbol represents one atom of the element. If more than one atom is present, we have a superscript follows the elemental symbol, showing the number of atoms present. Let's see an example. Carbon monoxide, carbon is 1, oxygen is 1, that's mono. Mono means 1. Nitrogen dioxide, you see, nitrogen is 1 because we didn't see any attachment to it. There was no any prefix denoting the number. We always put 1. Dioxide means two oxygen, di. That's what it means, 2 oxygen. We have water. Water is just dihydrogen monoxide. Again, is water. Sodium chloride, this. And then nitric acid. Nitric acid is 1 atom of hydrogen, 1 atom of nitrogen, and 2 atoms of O. This is H. Okay, HNO3, please. That's a correction. HNO3. Nitric acid. Let me make that correction. I just picked that one up. So this is nitric acid. Like I said, 1 atom of hydrogen, 1 atom of nitrogen, and 3 atoms of oxygen to make up our nitric acid. So the symbol, let's do reflection 1. The symbol calcium carbonate represents which of the following? Of course, here different elements combined together chemically, it represents a compound in this case. So reflection 2, it says, write the formulas for the following compound. It says carbon dioxide has 1 carbon atom and 2 oxygen atoms. The symbols have been given. We're not doing nomenclature now, so no need to panic. 1 carbon atom means capital C. And then, because that's the formula, use your periodic table, look at it, look it up. And then oxygen, of course, is O. But in this case, there are 2 oxygens. So we're going to, instead of you can say O2. That is wrong. You're going to say O substitute 2, carbon dioxide. We say the compound sodium phosphate has 3 sodium atoms, 1 phosphorus atom, and 4 oxygen atoms. So if you write the symbol. So to write it, what are we going to do? Start from sodium. I listed it in a way to be easy. 3 atoms, Na3 as subscript, 1 phosphorus, P, and then 4 oxygen atom, O4. So this becomes the formula of sodium phosphate. Yes. Yeah, let's do one more reflection on this before we let it go. Say a white solid glucose is made up of 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Write the chemical formula. So in this case, remember again, 6 atoms of carbon will be C6. Hydrogen will be what? 6 atoms of carbon, 12 atoms of hydrogen, H12, and then 6 atoms of oxygen, O6. That is how you write that. All right, we now go to classification of matter based on the physical state. So we want to classify matter based on the state. Of course, this is a physical state. All right, so matter exists in 3 physical states. Those are the solid, the liquid, and gas. So example of solid is something that is thick and does not really move around that much. Example here, we have wood. I'll write other examples. Ice blocks, good examples. Pencil, a pencil is solid. Diamond, the jewelry, the gold are all examples of solid matter. What about the liquid? Good example include water. We have water listed already. We have ethanol, which is alcohol. We have apple juice, of course. Apple juice. We have gasoline, gas you put in your car. All examples of liquid matter. And what about a gaseous matter? Oxygen is here already. The examples includes helium, is a good common example. Then carbon dioxide, the gas we breathe out. Nitrogen. Fluorine. etc. So those are common examples of matter. But let us try to understand the molecular representation of this matter and what actually makes them distinct, right? Of those three states of matter, like I said. For a gas, you look at the gas molecule, right? So the gas molecule here, molecularly, so this is the gas molecule. In the gas molecule, the atom, look at the individual atoms are actually given a lot of space in between one another. And they move around so fast and frequent. So the attraction, or what we call the cohesive force of attraction between these molecules is so weak. The attraction between one another is so weak that they don't even want to be close to another. They are so far apart from each other. Now, the liquid, on the other hand, is in the middle, is in the middle ballpark of this. If you look at it now, of course, they form molecules, but these molecules are much more closer to each other than what you find here for the gases. They are much more closer to each other. Of course, the gases do not take half shape. They rather take the shape of the container and fill it. The liquids only take the shape of the container to an extent that they can fill. You see, if this water. So, and like I said earlier, their properties are intermediate between the solid and the gases. On the other hand, if you look at this, the solid, you see the shapes here are so definite. These are ice cube, looks like a square. And you look at it, the shapes is definite. They're properly arranged in intervals. And look at the individual atoms. The individual atoms stay close to each other. They actually are their brother's keeper. So they are slowest in movement. They do not have a lot of space in between them. And they are properly packed. Because they are packed and the attraction is the strongest, that results to making them have a definite shape. So I'm going to go through a couple of those properties. In this table, I'm going to show you. This table, I made them. And this table is going to help. So here we'll list the property, what they have in solid, what they have in liquid, what they have in gas. So for the volume, solid do have definite shape, liquids having definite shape. And then, solid have definite volume, liquid have indefinite volume, occupies the volume of the container, and gases also have indefinite volume. What about the shape? The shape of the solid is definite. It can either be it's definite shape. You see the shape always in corners surrounded a square, a sphere. But the shape of the liquid is indefinite. It rather takes the shape of the container to the extent that it fills. Whereas for the gases is a different thing. It's indefinite. It takes the shape of the container and fills it completely. So if you put two mils of a gas inside a container that is big, it's going to fill it up because it's all constantly moving around. Compressibility, how much can you compress it? The compression in solid is low. It is medium in liquid, very high. Gases are highly compressible. Thermal expansion, on the other hand, the thermal expansion here is low because when you heat them up, the molecules begin to move about and lead to expansion. Here, the expansion is medium. Here, it is high because they can easily gain those kinetic energy and begin to move around and expand. Intermolecular attraction. The intermolecular attraction means the attraction between like atoms. Here it is the strongest because the atoms are holding on together about a fixed position. Here it is in medium or intermediate, and here it is the weakest. Gases do not really want to be attracted to each other. They rather fly around on their own to your tent. Everyone go stay on your own. And finally, the particle position. Here the particles are in contact and at a fixed position. The particles are always there, accounting for one another. Here the contact is, they're in contact, but not at a fixed position, not at a fixed position, but they're in contact. Yes. And finally, here, they are not in contact and they have at random positions. They're in random positions, they're not in contact with one another, they're flying around everywhere and doing their own thing. That is exactly what they do. They are just doing their own thing. That's what I said. So they do not hold each other accountable. They just go about their business. Now let's talk about the physical, chemical and physical state of matter. It's chemical and physical properties of matter. Let's talk about properties. Remember, properties are attributes. That's what we mean. Properties are, so first, let's talk about a physical property. A physical property is an attribute. Like I said, in this case, we're talking about an attribute. That's what I mean by a property. There are those attributes that does not involve the change in the composition of matter. Those things you can see, but does not lead to any change in what is in the matter. Common examples are color, size, shape, density, smell, texture, hardness, solubility, conductivity, melting, melting and boiling point, stretchability, all those stuff that if you look at them, they can change, but the composition of the matter doesn't change. If you leave them, they go back to what they are. On the other hand, the chemical attributes we're talking about, or chemical properties, will lead to a change in composition of matter. It makes matter to change from one matter to another into an entirely new substance. Example, it says something is highly inflammable. Inflammability is an example of if a chemical attribute of a matter that can easily burn. The pH, which involves acid and base reaction, which is neutralization, and then corrosiveness. When iron corrodes, that is, how much it corrodes is an indication of a physical property. On the other hand, this confuses students. Properties and changes. The properties, like I said, are attributes, but the changes are actually the process. All right? But let me show you this. You see, this is my colorful rose. This colorful rose here is an example of color. Color here, in this case, is a physical attribute. All right. For a change, physical change are those changes that does not involve the composition of matter. Remember, you're going to use the attribute displayed to see that. And some common of those changes will be if you're dissolving something in water, does not change the composition. Changes of state like melting, changes of state like melting, like vaporization. Melting is when a solid goes to liquid. Vaporization is when a liquid, of course, goes to a gas. Condensation, when a gas goes back to what? Liquid. Sublimation, when a solid goes to gas. Cutting stuff, stretching stuff. Those are all common changes that when they happen, they do not result into a new matter altogether, right? And because of that, what do we say? We say that physical changes are what? Reversible. They are highly reversible. You can get back what you started with without any change in their composition. What about the chemical changes? These are changes that result into change in composition of matter. It changes matter into a new substance altogether. It forms a new substance. Common example is burning of pepper. If you burn a pepper, it turns into ash. That's a different thing altogether. Burning of magnesium metal, acid neutralizing a base, rusting of iron, and all the rest of them. Of course, this is almost irreversible, but can be reversed only by chemical means. Can be reversed by chemical means, which takes time and energy. By chemical means alone, and not all of them actually. So can be reversed by chemical means. And common example I have here, the melting of an ice here is a physical change, whereas the burning of food here is an example of a chemical change. Let's do some problems here. Let's try to bring in some problems here. It says classify the following changes as either physical. If you are physical, you put P. Chemical, you put C. If a match is burned, if you burn a matches, it is a chemical change because that's what? Combustion reaction. That's combustion. Combustion reaction. Iron is melted. If iron goes from solid to liquid, it did not change the composition of iron, so this is just physical change. Limestone is crushed. This is a physical change. Crushing simply means breaking down or reducing in size. You are just reducing it in size. You're reducing it in size. So you're reducing it in size. Let me write that already. You're just reducing it in size. And then finally, if a limestone is heated, it produces lime and carbon dioxide. You see, producing entirely new different things. So actually, this is a decomposition reaction. This is called decomposition. And a decomposition reaction is a chemical change. What happens here is that limestone itself, calcium carbonate, is heated. The triangle shows heat to form lime, calcium oxide plus CO2. This is gas. This is solid. This is solid. So this is a chemical change because an entirely new substance has been formed. Let's take more examples here before we leave. Classify the following as physical or chemical change. Again, we're going to put C or P. A copper roof turns blue here is a chemical change because copper here is undergoing also a type of rusting. That's why it changes and turns blue over time. A nail is bent. If a nail is bent, nothing happens. It's a physical change. And a sugar dissolves in a cup of tea. Here is also a physical change. And you can always pause this video, try out these things yourself, and then come back and check for your answer. So let's finish with the last concept we're going to bring in here because we're already talking about matter. So you see, this law is a natural law that states, this law was actually proposed by Antonio Lavoisier, and the law states that matter can neither be created or destroyed in a chemical reaction. What it means is that if you start your matter now, like you're burning your wood, that at the end of the day, after burning your wood, that your wood forms soot, forms ashes and gases, that the amount you started when you burnt your wood, when you measure the mass, will be equal to the amount you ended. So on the other hand, it has to be a closed system. You have to assume that it's a closed system, that nothing is lost. It has to be a closed system that nothing is lost. So if you're burning a wood now, so if a wood burns like here, if a wood burns, right, what is in the wood? So the mass of the soot, remember it forms soot, mass of soot, you have to account for it, plus mass of the ashes, you have to account for the ashes, plus the gases given out, which is the carbon dioxide, and vapor, has to equal the mass of the wood when you started with, mass of wood plus the oxygen. That's where it started, plus the oxygen you used to burn it before burning in a closed system. So what that simply means is that this is the reactant. The reactant mass has to equal the product mass, despite the fact that a new substance is formed. Remember, this is a chemical reaction, a chemical change. A chemical change. A chemical change happened, but the total amount of the reactant and the product. The reactant is the chemical, is the compound or the matter that is undergoing a chemical or physical change, whereas the product itself is a new substance formed as a result of the chemical reaction. So in this case, the amount of this, when you measure it in mass, let's put it in mass, the total amount of this in grams has to equal the total amount of the product in grams. So this is what we call the law of conservation of matter. Let's take an example here. So this law is trying to make us understand this question, rather, this last question reflection says, understand that matter is never lost or gained in a chemical reaction. It says 2.3 grams of carbon dioxide combines with calcium oxide, which is lime, to produce 8.9 grams of calcium carbonate. And no mass is lost. So we assume that no mass is lost. You say, what mass of calcium oxide was involved in the reaction, and assume that the law of conservation of mass, it takes hold. So first, let's write the reaction. Here, if CO2 gas combines with calcium oxide, which is solid, it will form calcium marble, calcium carbonate, which is solid. So in this case, the total mass here has to equal the total mass here. So if we started with 2.3 here grams of carbon dioxide plus, let's call this X, we don't know the mass of calcium carbonate. This has to tell us to be equal to what? 8.9 grams. If we solve for X, what are we simply going to do is to subtract 2.3 from 8.9. So this is going to be 8.9 grams minus 2.3. And when you do the math, it's going to give you 6.6 grams of calcium oxide was involved in this reaction. So in conclusion, 6.6 grams of calcium oxide we combine with 2.3 grams of carbon dioxide to form 8.9 grams of calcium carbonate according to the law of conservation of mass. Because in this case, the total mass of the reactant equals the total mass of the product, obeying the law that states that matter is neither created nor destroyed in a chemical reaction. And having said that, we've come to the end of our lecture. Thank you for listening. Bye at this time.